So hello everyone. We continue with the Math102 Recitation Lab Week 10. And in this presentation, we will do the exercise at the end of Week 9 about the area of the surface of revolution. And we'll talk about integration by parts and trigonometric integrals, which correspond to sections 8.2 and 8.3. So we'll have two examples and we'll leave one exercise for next week. So the exercise at the end of Week 9 presentation was about the area of surface revolution. Here is the exercise. It was example 3. The curve y equals square root of 1 plus ex, when x is between 0 and 1, is rotated about the x-axis, and we'd like to find the area of the resulting surface. We will upload the file for Week 10 here, Week 10 exercise, and import the packages and the functions needed, of course, as usual. So we define the variables x and y using symbols as usual from SymPy, and notice again that x and y need to be real numbers. And we'll compute the surface area using that formula, which is S as the integral from a to b, 2 pi y times the square root of 1 plus dy with the x squared dx. This is because the revolution here is about the x-axis. And so the radius of the revolution is given by y. If the rotation is about the y-axis or a vertical axis, you should take into account that the radius would be about x. Okay, so we'll start by importing everything from SymPy to avoid any issue and to be able to move directly using or calling the functions directly. Now, x is symbols. It is a symbol which is real. We define y as the square root of 1 plus ex. As an our function, we'll display y here, square root of ex plus 1, everything is okay. And we'll compute 1 plus the derivative of y with respect to x squared, which is the term under the square root here in the integral. And we'll simplify it in the most simple way, so we get this result. And then we multiply y by this result. So this result is multiplied by y. Since y is the square root of 1 plus ex, this is what we get. Okay, so we are almost ready to integrate from 0 to 1, which means from a to b, the y times square root of 1 plus dy with the x squared. And here is what you get once you integrate, and you will already observe that it's not like in a numerical form. Okay, if this happens to you, which is normal, what you could do is you can just call the command do it. So this is what we are saying here. When SymPy returns the answer in the form of an integral, so we need to be much more precise, much more strict with it, and we use the command do it command, so it can help obtain a final answer. So we'll do the same thing. We'll call the function integrate, and we'll precise that we want it to give us a value. Do it. So of course here the integral would be half of plus e over 2 is the result of this integration. Okay, hope it's clear for this, and keep track of all the new commands we learned. We then, of course, we're missing 2 pi from the formula. We'll then multiply by 2 pi to get the final answer. So the area of surface of revolution is here 2 pi times that integral. Doesn't do it again, and this is what you should get. 2 pi times 1 plus e over 2, which means that the final answer would be pi times 1 plus e. Okay, so this is the first for the example at the end of week 9. And here it is from the Jupyter Notebook file. As you can see here, we can enlarge a little bit. So we defined our variable x. We computed the 1 plus the derivative of y with respect to squared, simplified, multiplied by y, and cell number 4. We then integrated, and we got exactly what we had in the slides after integration by 0 and 1. So we didn't get, a numerical value or a simplified value. So that's why we are in cell number 6, we are calling do it. And here is what you get, alpha plus e over 2. Then we'll just multiply by 2 pi. Okay, so hopefully it's clear for everyone. So we'll move on with the new material for week 10, which is about the integration by parts. So the example 1 is this example from 8.1, the integral from 0 to 1 of x squared plus 1 times e minus x dx. So we need to be very precise here that we would like to learn something new. or we don't want just to execute or to call the integration command, it would be not worth it. So first of all, we will evaluate our integral directly to be able to compare with the result we get with the parts integration. So we'll define xy as simples as usual after importing everything from SymPy. We'll integrate x squared plus 1 times exponential of minus x from 0 to 1, and we get 3 minus 6 over e. Of course, this is not the goal of the lecture or the recitation. The goal of the recitation of the lab is to learn something new. And here is how we can learn something new. First of all, from our integral, we need to understand what should be canceled. And here, the obstacle in my integration is that x squared in front of e minus x. So we'll define u as x squared plus 1, as you can see here. We'll assume that u is x squared plus 1, and dv is exponential minus x. And so from the integration by parts formula, you will see that d would be the derivative of u, which is 2x, and v should be the integral of exponential minus x. So once we defined u as x squared plus 1, dv as exponential minus x, du is the derivative of u, and v is the integral of exponential minus x. You could also put here just dv. And the result of our by parts integration would be res, here, res for result, as uv minus the integral of v du. Okay? And you know very well the formula. So res here is defined as uv, once you plug in x at 1, of course, minus the value at 0. So it's uv at 1 minus uv at 0. So this is the first part of the integral. And then the second part is that's the integral from v minus of v du from 0 to 1. Once you execute this, this is what you get. You get minus 2 over e minus the integral from 0 to 1 of minus 2x e minus x, e to the power minus x dx plus 1. And you could already say that, well, here I'm not going very far because this one requires, again, an integration by parts. So this result requires, again, another integration by part. And what you could do is, again, you can assume that u is 2x and dv is e minus x, and you go another way, and you just compute this again with the integration by part. Here, we'll cut it short, and we can directly do it again. But instead of doing it by the integration by part, I take the integral we got here and just call do it again. I insist on this command again. So I'll get exactly my result, but at least I used integration by part once. And we obtain exactly what we got, what was expected, which is 3 minus 6 over 2. From our Jupyter notebook, you can see this is example 1. This is how we called everything from SymPy. We defined the variable x, the integrand at x squared plus 1 times e minus x, integral from 0 to 1. We got 3 minus 6 over e. Then we defined u and dv. We got du as the derivative of u, and v as the integral of exponential minus x. Okay. We defined res as uv at 1 minus uv at 0 minus the integral of v du from 0 to 1. So we got this minus 2 over e minus the integral of from 0 to 1 of minus 2x e to the power minus x dx plus 1. And that part, which is an integral, we are asking it again to be computed by do it. So it is exactly what you got in the slides, 3 minus 6 over e. Okay, I hope it's clear. I'll move to the next example. In the next example, we are asked to evaluate the integral of x tan inverse of x, or arc tan of x. And here, what you could, the idea is that we know about the derivative of tan inverse, but we don't know the antiderivative. So we'll define u as the tan inverse, and u then would be 1 over x squared plus 1. Okay, and if we define dv as x, so v would be half of x squared. So the integral becomes uv minus the integral of v du. And we can proceed. When we define res as uv minus the integral of v du, we get x squared, of course, which was from here, from the integral of v, x squared over 2, x squared to the power 2, x squared, yes, over 2 times arctan minus the integral of x squared over 2 times x squared plus 1. And this guy here, x squared over 2 x squared plus 1, could be simplified in a way that if you add here 1 and remove 1, you could write it as minus half plus 1/2 of the derivative of arctan. And the derivative of arctan, so we just need to integrate the derivative of arctan and get half of arctan. And this is exactly what we get. So the remaining integral can be written as half minus half of x squared plus 1. This is what I was trying to explain. And therefore, we can get automatically after integration and using simplify the following. X squared times arctan of x over 2 minus x over 2 plus arctan of x over 2. So this is the result of our integration. Okay, hope everything is clear. We'll move just to the Jupyter notebook. Here are the steps. First of all, our function x tan inverse. We defined u as arctan using a tan. A tan is the function in phi. We have to learn this, a tan of x. dv as x. du would be the derivative of u. V is the integral of dv. And we define the rest as uv minus the integral of dv. So this is what we get in cell 21. X squared arctan of x over 2 minus the integral of x squared over 2, x squared plus 1. And then we simplified it. And this is what we got. Now, about the evaluation, this thing that was missing in the slides, we wanted to evaluate, for example, what happens here at 2 and 3, or if the integral is from 2 to 3. So we evaluated this result at 2. Then we evaluated at 3. At 2 is 379. At 3 is 863. And if you do the difference, you get 484. So basically, this is the integral of from 2 to 3. Now we made it a definite integral from 2 to 3 of x tan inverse of x. We added something else to the slides. Okay. Hopefully it's all clear. We finished by this example 3. We'll leave it for next week presentation for week 11, where we are asked to use this to use integration by parts on this integral from 0 to pi over 4 of x tan of x secant squared of x. Thank you very much, and hopefully we'll continue very soon with our next recording.